Okay, so this is what node analysis looks like. No, I mean, yeah. Node analysis or node voltage method, same thing. So the node voltage method. So the process is defined, again, remember this is a process method. So step one is to label all extraordinary nodes. And we know what those are now. Extraordinary nodes are any nodes that connect 3 or more branches. So we're going to label them all. 1 is going to equal ground. And typically we just do that at the bottom of the circuit. That's usually the easy thing to do. And then we're going to define some variables. These are going to be the node voltages. Remember these? And so, yes, I'll come back to that. So define variables, and this is going to be equal to all the node voltages at all of those extraordinary nodes. So what that means is when we solve the set of equations we're going to get, the variables are going to be our answers. So this method will always give us voltage as answers first, and then we use that to find current or any other voltage we might need. So the variables are the node voltages. That means the answers initially are node voltages. So the third thing is we will apply KCL at all of these nodes except any that we already know the answer to. So we're going to apply KCL at all nodes. This is the important part, with unknown voltage. That makes sense, because if we already know it, we don't need to write an equation for it. We already know it. Importantly, so KCL, we can say currents in equal currents out. Some of the currents in equal 0. Some of the currents out equal 0. Those are all of our choices. We are going to use by convention, but also it works out great for the math. We're going to look at this. The sum of the currents out is equal to 0. It's going to make our math work out better with fewer negative signs. Okay, so if we have 2 nodes, we'll have 2 equations, 1 at each node, and 2 variables, B A, B B, say. If we have 3 nodes that we don't know, we'll have 3 KCL equations, 3 variables. So you can see this is where we get matrices from. So here we're just going to solve the simultaneous equations. Where we are happy to have calculators. Not everybody allows you to use calculators for this. That seems silly to me not to. So it's blunt. We're going to use the calculator for that. And then remember what that gives us. That's going to give us all the node voltages. So then our final step is to find the final answer, whatever it is we're looking for. Once you know all the node voltages, you know everything about the circuit. Likewise, when we get to the mesh current method, once you know all the mesh currents, you know everything there is about the circuit. Okay, so the last thing I want to point out is when we're trying to find some of the currents, so what are 3 different things that could be connected to a node? So we could have, connected at a node. Okay, we could have a voltage source. So we have a voltage source. Do I know the current through that?
No.
No, so I can't actually use that. But if I know a voltage source connected to the node, then probably I already know the node voltage anyway, so I don't need to write an equation. So importantly, the voltage source, the current is unknown, so you cannot use that. We're going to come back to that later in the class. We have a current source. Well, then the current just already is what it is, right? It's either going in or coming out. So that is exactly what it is. The last thing that we can have connected is a resistor. And so here, if we've got, say, node A, and there's a resistor between node A and node B, and we're trying to do KCL here, So our current out looks like that. We need to remember how to write the current through that resistor. It's always the first voltage you run into, so V sub A, whatever the voltage is there, minus the voltage on the other side, so that's your voltage difference, divided by R the resistance. So you want to do it in that order. The advantage then is that if we're doing KCL and we're always doing current out, V sub A, the node voltage is always positive, so it makes it easier for that. Does that seem okay so far? All right, so let's just do a whole ton of examples. I have a feeling there's got to be a better way than this. Oh, and I didn't get everything. All right. I'll be happy to know your heads are not in the picture. So here's our first example. And the first ones are going to be really pretty simple. So I said find V sub A. I'm going to call this A. I'll make it a little bit bigger. Okay, so before we get started, if I wanted to find V sub A, what are 2 or 3 solutions I could already know how to solve this with? What could I do? These are in parallel, right? And I know the voltage across either one is the same, so I can combine these, and then I just have current equals IR. So that's fairly, so one option is REQ for the parallel resistance, and then V equals IR. Anything else?
Do a source transformation if you really felt like it.
You could do a source transformation, and then you'd have voltage source, resistor, and then it's set up for what? Well, so if I have voltage source, resistor, and I just want the voltage across only this one resistor, it's perfectly set up for voltage division. Yeah. So I could do source transformation. And then that sets me up for voltage division. Oops, let me make it this way. So when I ask you to think about what are some other ways to solve a problem, that's as much information as you need. Because that gives you an idea of how complicated it's going to be to do. We're not going to do either one of those. We're going to do, everything we're going to do tonight is going to be KCL, is going to be node analysis. So first thing I need to do is identify all my extraordinary nodes. So where are they in this circuit? A and ground. Okay, you can draw on the ground if you want to. You don't have to. So I'm going to do KCL at node A. I recommend that you go ahead and let's see all that. I recommend that you write something like this, even if you just write KCL at A, so that way, as it just makes it easy for you to track and double check your work. If you need to do that, you kind of note to self what you did. Okay, so KCL, I'm going to do currents out. You do not need to draw those arrows in. I'm just doing that for now, just to remind us what we're doing. So I have a tendency, that's just me, to always kind of start on the left-hand side and move around towards the right. So this first current here, what is that current? It's a source. This is 5 amps going this way. So what number do I write down? -5, because I'm looking at it going the other way. So I'm going to start with -5. Now I need the current through this one. Do I know the current through a resistor? Sure, because V sub A is fine for me to use in my equation. That's my variable. So I'm going to say V sub A minus 0 over 3. You do not need to write the minus 0. I'm just trying to write so that you know what I'm doing. And so what about this one? V sub A minus 0 divided by 6. Okay, so clearly we don't need this part. A couple things you could do here. This, so nobody likes fractions, they're a pain. So one thing you could do is clear fractions. Let's just remember how to do that. That's not typically going to be the way we solve these things, but just to remind you how to do that. So to clear a fraction, you just need to multiply both sides of the equation by everything to get rid of all the fractions. So I'm going to say multiply the entirety by 6. So negative 30 plus 2BA plus BA equals 0. 3BA equals 30. BA equals 10. What I've gotten that, these in parallel are 2. 2 times 5 is 10 volts, so yeah. So I don't know that I would have chosen to do it using node analysis because it's kind of overkill, because I can do this in my head and then V equals I can do that in my head. So, you know, again, we're gonna look at each circuit and try and determine which is going to be our best plan. So this is the basic idea. All right, so let's look at another one. Very much the same, I just only thrown another resistor in, and I've made it a voltage source. Okay, so the first order of business again is to identify extraordinary nodes. I've got extra components now. How many extraordinary nodes are there? 2. One here and one here. So again, I'm not going to draw in ground this time, just because I know I'm not going to work with that. Our options, I think our options are still parallel combination and then voltage division. Oh, piece of A. So I could do parallel and then voltage division. Again, that would probably be the one I do in my head, because I can do that in my head. But let's do KCL instead. So I'm going to do KCL at node A. Go ahead and write it out. You guys write it out and then see. And if it helps to put ground here, so that you can draw what the voltage is at this node, that's fine. So if you would like to label this, do we agree that that would be 5 volts? If I've made that, if I've made this ground, then this is going to be 5 volts. Okay, so now go ahead and write KCL equations. Current out. And let's say, in addition to finding V sub A, let's say I also want to find I sub 3. Let's say let's find both. Okay, does this equation look pretty good? Let's look at another way to write this. I know eventually I'm going to get V sub A on one side and everything else on the other. So this is another way you're going to see me write it very often, because it's so easy to throw this in our calculator that there's no reason to do. Typically, so these happen to be really nice resistors. How often do we have that? Not very. So trying to clear fractions is not a good long-term plan. That just only works sometimes. So here what I'm going to do is I'm going to take V sub A and factor out. I have 1/3 V sub A, 1/3, and 1/6. So I'm going to write it that way. 1/3 plus 1/3 plus 1/6. And then I'm going to put everything else on the other side. So 5/3 on the other side. You could clean up these fractions, but let's not. Let's look at what the calculator will do for us. Let's see that. So I'm just going to put in 5/3. So 5 divided by 3 divided by, open parentheses. I'm going to divide by all of this. So I'm just going to say 3 and hit that -1 button, plus 3, hit the inverse button, plus 6, hit the inverse button, finish my parentheses. Does that look like the proper thing? 5/3 divided by this whole thing. 2. Or you could mess with the fraction. I'm thinking that's really easy. So yeah, take a moment, make sure that you can do that. We're going to do this a lot. We're going to enter all of our matrices this way. We're not going to predetermine, pre-calculate. We're just going to let the calculator do all the work for us. Does that come out right? No? Yes? Yeah, no, but a third and a, 2, 3. I'm thinking that was a 6, sorry. Yes. Yes. So V sub A is equal to 2 volts. So this is a pretty powerful process because you just throw the process at it. You don't have to hunt through what do I know first and what can I transform into what. We need to know all of that because we're not done with that. But this is an excellent process method. All right, so now what if we wanted to know I3? Do I have enough information now to find I sub 3? Well, yeah. Remember, once you know V sub A, once you know the voltage at all the extraordinary nodes, you know everything. So I sub 3 is just the first voltage minus the next voltage divided by the resistance. So I sub 3 is going to be V sub A minus 0 over 6. I misspoke. So 2 minus 0 over 6, 0.33. So again, pretty straightforward process. Any questions on that so far? It's going to get harder. Okay. So let's look at this question I have at the bottom, which is, what if the 5 volts were, if you had a 5 volt source just in parallel with the 3 ohm and the 6 ohm, and you wanted to know V sub A? So in other words, if you just had the following. It's known, right? V sub A is 5. There's nothing to do. So just remember that if you've got a voltage source that can, if your voltage is known, there's no equation to write. So here we know V sub A is equal to 5 volts, done. Okay, so just a reminder that don't make it harder than it needs to be. So we only write KCL for nodes where we do not know the node voltage. Okay, so get another one. Okay, so here we're trying to find V sub X. Here, we have a dependent source. That does not change anything. It doesn't change anything. We just write down, it's got a little bit more in the way of symbols, but fewer numbers, more symbols. Sorry. Because it's got a dependent source, I'm not sure that I really see another really great option for solving this. I could do a source transformation, connect they're in parallel, then that's in parallel. I guess that might work. Yeah, maybe. Anytime I have dependent sources, I have a tendency to not want to do too much in the circuit. But instead, let's look at KCL then. So, how many extraordinary nodes do we have? 2. So ground and here. This is not extraordinary. So we've already got V sub X labeled. So we're going to do KCL. So how many branches are coming out of that node?
4.
4 is correct. From this node, you see this one, and this branch, that branch, and that branch. Those are all, because remember, this is one big node together, so we need to look at everything that comes out. So there are 4 branches in that. So this is one big node. Okay, so 4 branches. So V sub X, minus 6, because we know if this is 0, then this point right here is 6 volts. If you need to write that in, go ahead. So we're going to have V sub x minus 6 over 2. That's V sub x over 3. What about this one? Do we know the current in this branch? Yeah, it's 2 V sub x. So you want in or out? It's going in, and I'm summing everything going out.
Negative.
So it's going to be negative 2 V sub x. So you don't know the current, except you do. You have an expression for the current, that's sufficient. And then we have V sub x minus V sub x minus 0 over 6. So again, if you only have one extraordinary node, you have one equation and one variable. So much easier than any other process you could think to solve this particular circuit. This is hands down to me the easiest way. So now I just need to collect all my V sub x's on one side, everything else on the other side. So I have a half and a third minus 2 plus a sixth equals negative 3, positive 3. A half and a third and a sixth. Anyone happen to know what that is? But let's say you didn't know that. So you put it in your calculator. So again, I'm going to take 3 divided by, open up parenthesis, 2 inverse plus 3 inverse minus 2 plus 6 inverse, finish in parentheses. Does that look right? Negative 3, which I know because if this is 1, and that's negative 1, so negative 3. So we're going to get then V sub x is equal to negative 1 volt. Yeah.
Why again is it negative sub x minus 6 for the first one?
Oh, right, because I want the current through this resistor. So if I want the current here through this resistor, it's the voltage drop across the resistor divided by the resistance. So the voltage drop across the resistor, this is V sub x here. This is V sub x here. This is 0, which means this one must be 6. So V sub x minus 6, because this is 0 here. For all the other ones, V sub x, the other side is 0. V sub x, the other side is 0. So again, if you can think about your current through your resistor is the voltage on the near side minus the voltage on the far side divided by resistance. Yeah.
Earlier when you said the first one we come to would be the positive, or I mean the first term, and then you subtract the second side of the resistor?
In the order of the current.
Of the current, okay. So like if we were trying to figure out the first node's current, then it would be 6 minus Vx instead of
If you're
Vx
trying to
minus
go
6.
this way, if you defined your current that way, it would, so it's always in the direction of the current. So because we're summing currents going out, that's how we're doing
The
it.
node current, for that, like not the real,
Yeah, no,
thing.
no, no. Right. So this only this current definition is just for the process.
right, so if I was
Yeah.
looking for that first node that's 6 volts,
Yeah.
then the arrows would be that way.
Yes.
The other way, so it would be
yes.
6
Except
minus.
we just wouldn't write one here because it's not extraordinary. But
Right,
yes, right.
okay.
Correct. So it's always in the direction of the current. So we have defined, so for the process that we're doing, we define all the currents out. So that tells us that the advantage to that then is that the first node is always the node voltage, the variable. So it's going to be V sub x minus, V sub x minus, V sub x minus. So all your V sub x's are always positive. That just makes it a little bit easier.
Why is that first one down on the right-hand side, right next to the source? Why is that one down? I'm sorry.
Like they're all out. So
Okay.
so remember we're doing for KCL we're doing the sum of the currents out is equal to 0. You got to pick something and stick with it. So we're just going to always do current out. Yeah.
Okay, so basically, if there's any type of defined current direction for this particular process, you're ignoring.
Correct.
Okay.
Yes. So let's say I was trying to find the current for this current source. Let's do that. So we want to find this current. So V sub x is -1 volt. So -1 times -2 is -2 amps in that direction, which is really 2 amps in that direction. So it's one, yes, so Cody's question was, whatever I'm trying to find, I ignore for the purposes of the node voltage process. For the node voltage process, to find just the node voltage, I set up all my currents going out. Once I know this, then I go back and revisit what am I really trying to find. So let's do another one because I think that's what's coming next. All right, so let's look at this one. If it's not going to explain that. Perfect. The next one. Okay. So why don't you? So let's just quickly talk about what we expect here. We're going to set up the two equations, two unknowns. I just told you what we expect here. And then we'll revisit matrices. So what I would like for you to do, we agreed that, and these are pre-labeled for us if you wanted me to. I tend to label them A and B because our resistors we tend to number. And so when I say R1, then V1 is the voltage across R1. So I tend to label these as A's and B's. So I may just go ahead and change that for myself and make that VA and VB. And I just, sorry. Okay, so what I'd like for you to do is to write a KCL equation at V sub A. Actually, let's do this one together and then we'll work with the next one. So we're going to write two KCL equations, one at A and one at B. All right, so KCL. And here's where we're going to get to the difference in direction and current. So let's just start with this one. I'm not going to draw a current, well, I guess I could. I'm not going to draw current arrows on. I just know I'm summing out. So this one, this first one, is V sub A minus 21 divided by 5. Because I'm assuming that ground is down here. So first I have, so KCL at A. So I have V sub A minus 21 over 5. V sub A minus 0 over 10. Let's see if I can make it a bit smaller. And then I have V sub A minus, what's on the other side? V sub B, write it down. That's fine. You're going to have two equations in two variables, so it's fine to use them both. So V sub A minus V sub B over 10, and that equals 0. Yeah, it is over 5. Yes, thank you. That's pretty good. That's my first mistake of the evening. I'm tired. Impressed. All right. Okay, so now we need to do it again, but from the perspective of V sub B. So now we're going to write another equation, KCL, at B. So again, I can start on the left, your choice. If I want the current coming out here, it's V sub B minus V sub A over 5. That's okay. It's just from the perspective of node B, that's out. So V sub B minus V sub A over 5 plus V sub B minus 0 over 10 plus, now we've got to be a little bit careful, V sub B minus, what is this value here? This is 0. Yeah, this will be negative 10.5, so when I subtract it, I'm going to subtract the negative. Yeah, so let's just point out that this right here is negative 10.5 volts. Is sitting right there, assuming that ground is here. So I'm going to say, I'm just going to write it out kind of in detail. V sub B minus negative 10.5 divided by 5. So 2 equations, 2 unknowns, lots of fractions. So our options are, clear all the fractions and use substitution. Clear all the fractions and use elimination. Or matrices. Matrices are our friend. We've been over those in lab a little bit, so let's do them again.